Hello, everyone. Today we're going to be talking about how Databricks and NVIDIA got together to cut costs and boost speed when it comes to next-gen DICOM imaging. I am Douglas Moore, HLS Lead SSA here at Databricks. First off, let's talk about the challenge facing medical imaging industry. Data growth consistently strains medical imaging workflows, whether it's local PAC storage or moving it to the cloud and the bandwidth required. A lot of this is overall growth in the industry, projected to move from in 2023 from about $40 billion to about $80 billion in 2030. The second challenge is with large, fine grain, thin slice visualization of 3D CT scans, MRIs, PET scans, and so on. Visualization performance is critical in terms of the workflows that clinicians go through and the overall usability. And then the third challenge, and actually opportunity, is knowledge information extraction. Must be both efficient and near real time to apply AI to these large 3D scans. All right, how are we tackling these challenges in the medical imaging industry? Databricks has this solution accelerator for medical imaging called Pixels. It facilitates ingesting, managing, governing massive DICOM image data sets within our Databricks Data Intelligence platform. NVIDIA, with strong support for accelerated computing and open source projects such as MONAI, MONAI being a state-of-the-art AI modeling, training, inferencing platform, what we decided to do is get together and develop HT-J2K compression for these 3D images. With this compression, we shall see many benefits. But first, let's talk about our approach within Databricks Pixels 3.0. First off, we ingest data, DICOM images, typically land that in our governed volumes, which sits on top of S3 bucket in the AWS cloud. Second is that we'll pass it through the HT-J2K or high throughput JPEG 2000 compression algorithm accelerated by NVIDIA GPUs, and we'll write out those compressed and coalesced files. Then we'll index the files like we do in Pixels, and we'll store that in a Delta Lake table. Again, all this data is stored in the customer's S3 bucket. Now that we have a structured index and the binaries for the DICOM images, those can be passed to a viewer, Open Health Imaging Foundation or OHIF viewer. They can be passed to segmentation model powered by the MONAI organization, and they can be passed on to other Databricks applications, AI, BI dashboards, Genie spaces, customer-built cohort builder apps powered by Lakehouse Databricks apps. This data could be managed and tagged with data contracts apps. Visual language models can extract and detect PHI. They can extract other information description of these images, and classic ML models can be used to segment, to classify, and extract or predict parameters like breast tissue density. So one customer, UC Davis Health, has this public quote for us. They use the Pixel Solution Accelerator to ingest DICOM images into our Databricks environment, and then using the Lakehouse platform, support faculty and staff in terms of building out their research projects. Now, with all this talk of HT-J2K, what exactly is it? Well, look at this diagram here. Assume A is a full high-resolution X-ray or 3D scan. Through encoding and then compression and then progressive decoding, we're just downloading a few bytes of that. You can get a low resolution representation of the full image. Download a few more bytes and you can double the resolution. And then this continues, so on and so forth. So with this, high throughput progressive decoding, you can render a full high-resolution image in a progressive manner. What this does for the end user is that it makes them feel like the system is very responsive and very fast. Overall, HTJ2K provides about 4x compression for uncompressed image. So we are going to see that additionally, one of the value factors here is driving efficiency with MONAI label, with segmentation workloads and other AI workloads. We saw overall an 81% speed up in the time in the active learning loop and the segmentation time with this particular model. A good sized chunk of that was due to the compression. And then also working with the NVIDIA team, they helped us optimize our pipeline further with best practices. The results of that was before it took 11,000 seconds to run inferencing to segment these 3D scans here. Over 140 for like CT scans, PET scans, so on and so forth. After compression, after best practices were applied, it took only 2,000 some seconds for a net of 81% faster. This will definitely help with the real-time inferencing that can be driven from the OHIF viewer. We can inference also much larger 3D scans with this improvement. The second one is optimizing storage. Two-part strategy here. One is that we coalesce multi-DICOM file series into a single multi-frame DICOM file for the CT, MRI, and PET scans. We then applied the HTJ2K compression codec via NVIDIA's image codec library to reduce the pixel data. This compression reduces the storage footprint. It also, with fewer bytes, you end up with a faster transfer of data into your AI models, into your viewer. Our results here for a zipped archive of the MIDI-B test validation set for 1,233 images. Zipped, that would be 19.3 gigabytes. Uncompressed, that's almost 3 times larger at 57 gigabytes. Taking the uncompressed and then applying HTJ2K, we get to 14 gigabytes. One thing to note, the zip files are not generally compatible with the AI models, not compatible with the viewers, whereas the uncompressed files are, and also the high throughput J2K compression algorithm. Those coalesced files are compatible with the viewer and with the AI models. So the next value point here is accelerating the visualization. We want to go for sub-second retrieval. We want to handle much larger 3D scans with this. By lowering the latency in retrieving and decoding the images, we want to improve the user experience there. Our results before with multi-file 3D scans, you can see each file is approximately half a megabyte, takes about 1 second to download. That ends up being 188 requests to the server for a total of about 34 seconds. Whereas after compressing, after coalescing, we get down to a 26 megabyte file. All these files over here are about 94 megabytes. Much lower fetch here. We end up with 3 requests. 2 are metadata requests, setting the parameters for Cornerstone. And then the third one is the download of the full file. And kind of a total, download and decode and render time is now 20 seconds. Pretty good improvement overall. So to wrap up these 3 value points that we got out of this joint project between Databricks and NVIDIA, we see 81% less segmentation time for Vista 3D. Vista 3D is that model can produce about 130 labels from, say, a big chest CT scan. 40% faster image download time and 75% less storage. Think about that. That's like storing 4 petabytes of data for the cost of 1 petabyte. A big improvement there. So let's thank the team here. I, Douglas Moore, am leading this initiative on the Databricks side. Our lead engineer is Emmanuel Rinaldi, and our chief data scientist on this project is Yen Lo. And I would like to thank the NVIDIA Image Processing, QSIM, and MONAI engineering teams led by Wokin, Makan, Rahul, and Sebastian. Thank you very much, NVIDIA. Thanks, Joel and Mayank, for your special support in pulling these teams together. And for further information to try this out, go to our GitHub page. You can use this QR code. And with that, thank you very much. And we will see you on social media. We'll see you in GitHub. Reach out to your account teams and we can connect and dig deep into your use case.